All right, hi Algebra 2ers. I hope the AP went well. This is a quick overview of Notes 15-1 for you guys. So on the first page, that's just some fast review from yesterday. The idea that, when it's all mounded in the center, that's your bell curve, that's your normal distribution. If it trails off to one side, that means it's skewed one way or the other, or in this case, skewed to the right since the tail is on the right-hand side. As for the next one, it just talks about the mean of the women's heights being 64.6 inches. Standard deviation is 2.75, and this is meant to represent the distribution of the heights of 1,000 women. So when it says interpret it in context, I'm not going to go over that one with you, but the idea that you recognize, like what's your X bar? What does that represent? And then what is S of X? What does that represent? So you can see the filled out notes for that, but I think you can handle that one on your own. The next page just says, okay, now let's take those distributions and what do you notice about like what percentage fits in between here? The idea with this is just supposed to show you that if you add up all those frequencies in between, right? So you end with like 0.10 is like this guy right here. The 0.12 is that next one. 0.14 is this one up top. 0.13, 0.11, and 0.10. Those are those three respectively. The total sum comes out to be about 0.705, or it represents about 70-ish percent, right, of the people. So when it says when you refer to the normal curve, so that's that separate sheet that you're getting. It says add up the percentages that are one standard deviation above or below the mean. Well, that means in the curve, when you look at the bottom, the ones that go from -1 to +1, when you add up all that in here, what you should end up with, right, is adding 15 plus 19.1 plus another 19.1 plus 15 again, and you get 68.2. So what we're saying is that the height model data that is normally distributed. So when it says, are the sums close? Well, heck yeah. All right. And are they close enough to assume it's a normal distribution? In this case, yeah, we can say yes. All right. So the bottom of this is just some practice in identifying the different shapes. So that's the stuff that we had talked about yesterday. Does it fit normal distribution? Is it skewed? Is it a uniform distribution? I'm going to jump right over those to talk about what's on the next page here. So when it says when the distribution is normal, we can use z-scores to standardize any data set. So a z-score, it's not an actual like grade, it's more the idea of how far away or how close to the mean is that particular score. Right? So a ton of things can be represented with z-scores. Heights, weights, blood pressures. They can do it with standardized tests like the SATs, things like that. Right? So when it says a z-score is the number of standard deviations away from the mean, when you see that normal curve that you guys have, and it's got the numbers that run from -3 over here up to +3. Those are z-scores. That's what those values are. Right? So how you calculate the z-score is it's calculated by whatever the observed value is minus the mean value and then divided by the standard deviation. And that will tell you how far above or how far below the mean it lies. All right, you got to remember the mean is dead center. That's where your mean is. Right? So a positive z-score just means that you are above or greater than the mean. A negative z-score, you're going the opposite. So you are below or less than the mean. And it kind of depends on the context as to whether or not that's good or bad. With blood pressure, you don't want to be above the mean. You'd rather be below it. If you're talking test scores, you want to be above the mean. You want to do better than everybody else. Okay? So for this, all this is talking about is femur length. They're saying the mean is 17.5 inches. Standard deviation comes out to be 1.3 inches. Just calculate the z-scores for each. Right? So for an 18, that's above the mean. So it should give you a positive z-score. So when you calculate it, 18 is considered the observed value. So 18, and then you're going to subtract the actual mean. to the 17.5, and then divided by the standard deviation of 1.3. And so when you take that difference divided by 1.3, it comes out to be 0.38. So what that means is that that length is 0.38 standard deviation above the mean. All right. So it's meant to represent that you are above the mean. So it's longer than the average. And so you can go through, there's a whole bunch of them. I'm just going to do 2 with you here. Okay. So if we plug in like here at 15, if we do 15 minus the mean of 17.5, you get that difference and divide by that. You're 1.92 standard deviations below the mean here. So that's significantly shorter. When you think about like a normal curve, right? Almost 2 standard deviations below, if here's the mean, it's like way down here, right? At like -2-ish. So it's pretty rare. The more common are going to be the ones right here down the middle. The more rare ones are going to be the ones at the outer extremes. And so it just kind of tells you where you lie in terms of how close you are to the mean and how out of the ordinary that value would be. So when it says down here, what seems more likely, a length of 20 inches or a length of 17.4 inches, and explain? Well, what you want to do is you're going to calculate the z-scores and compare. Now, for 17.4, you'd plug that in here, and then minus your mean of 17.5 over 1.3. And then for the 20, plug that in, and over the 1.3. This one comes out to be just a hair less than the mean. This one comes out to be significantly greater than the mean. So when it's saying which one is more likely are the values closer to the mean. So this is the one that's more likely. Okay? And you could say because it's closer to the mean or it's closer to 0, however you want to think of that. And so if something was on the mean itself, it would be at z equals 0. So that's how you actually calculate the z-score. We're just going to do 1 or 2 of the other problems together. So when you flip to the next page, this one, let's see. Yeah, we can do this one here. Given the average battery life of a Duracell AA battery is 21 hours and a standard deviation of 2 hours, the battery you tested has a z-score of -1.25. All right. It says without calculating the battery life, what does a negative z-score tell you? Okay. So anytime it's negative, I want you thinking it is below the mean. So the mean in this case is the 21 hours. So in terms of this problem, that's bad. You want the battery to last as long as possible. This is below the mean. So how many hours did the battery actually last? All right. In that case, you would have to calculate, right, the observed value that correlates to z equaling -1.25. Okay? So just use that same equation, and you're just going to plug in for the parts that you know. So the equation is this again. So I'm sort of shorthanding here. All right, so there's our super shorthand. All right, so if we plug in, we know this is -1.25. So we want to go x for the observed minus the mean of 21, and then over what's our standard deviation here? 2. Right? And then you can simply cross multiply, solve, however you want to do this. So this is going to give us -2.5, and then x minus 21, and then you can add 21 on over. So when you add 21 on over to the other side, oh geez, what is that going to bring us up to? -2, so 18.5. So that's how many hours that the battery actually lasted. Same type of things going on with the next one. It's talking about your iPhone 5. You can tell these notes are a little old. Lasted for 3 years and stopped working. And it says with a z-score of 1.11, what's the standard deviation of phone life? So again, in this case, you're plugging in for the parts that you know. solving for the part you don't know. So in this case, you're going to solve for the standard deviation, the bottom part of it. So you can look online to kind of see some of those guys. The last one I'm going to look at, I like this one, is talking about the SATs and the ACTs. So it says you took the SATs and the ACTs. You scored 1140 on the SAT, 25 on the ACT. All right, so there's your SAT, there's your ACT. It says you're having a hard time deciding which score you should send to the colleges you're applying to. You only want to send the best score. So the mean SAT score, so I'm going to split this here. So SAT, ACT. All right, the mean here is 1,000. Standard deviation is 100. Right? And standard deviation can also be used with that little sigma. So sorry if I interchange those, that's what's going on. The mean ACT score is 20.8. Standard deviation, so this or this, however you want to think of it, is 4.8. The whole point of the z-score is when you're looking at two different formats, it brings them to the same format, so they're speaking the same language, basically. All right. So over here, the z-score, well, they got an 1140. Subtract the mean of 1,000, divide by 100. Over here, they got a 25 minus 20.8, the mean, divided by 4.8. Okay. So I'm actually going to grab my calculator, so I don't have these ones done out. So the first one would leave us with 140 over 100. Oh, that was sort of silly. I didn't need my calculator. This one comes out as 1.4. So it's good. You're above the mean, which is good. Right? Over here, if we do 25 minus 20.8, you get 4.2. Over 4.8, you get 0.875. So comparatively, you did better on the SAT compared to everybody than you did on the ACT. I mean, you definitely did better than everybody on both, but this is your top score. So you're looking for the higher z-score to be able to compare them directly. Right? So it's sort of like if I was measuring somebody in inches and somebody else in centimeters, I need them to be speaking the same language to be able to figure out which thing is bigger. That's what the z-score allows you to do, is to get everybody into that one standardized language so that you can compare. Right? So in the case of who's better, you want the bigger z-score here. All right, homework tonight. You should have picked up the worksheet. You can use the bell curve just as a reference if you need it. Otherwise, use your calculator. You can calculate those little z-scores, and we'll pick up on Monday with day 2, and then how you can do some of this work on your calculator. All right, see you guys then.